So I'm also sorry for those of you that came to this track hoping they would hear more about machine learning. But I think this is the last talk about it. So what is it that I'm going to describe? I hope you remember well what I talked about at the plenary. I'm going to give you more details of those couple of slides in that talk that were discussing how we want to do fast simulation in GeantV, and in particular developing a machine learning tool for that. The introduction you should know very well already. I will not go through this again. Let me stress simply the fact that, yes, fast simulation is already used, and it will be becoming more and more important with the new runs, the high luminosity LHC. And again, current solutions are often very detector specific. So this is something that we don't like, and we would like to provide a generic interface to address this issue. The idea is that we would like to provide something that is easily configurable, probably based on the style of what is it now in GeantV user actions. We would like to have to provide solutions that are composite in the sense that something that will allow you to mix easily fast and full simulation within the same event, or for different regions of your detector, for different sub-detectors, or the kind of particles that you want to simulate. And also give a choice of basic tools that include machine learning tools, but also would be compatible with other more standard or tools that have been already developed and are being used. Yes, I can't move on from here. Yes. So you've also seen this. You followed Andre's talk. I don't need to explain how GeantV works. The point is that including in this new schema fast simulation would be straightforward in the sense that this would just be an additional stage that could behave exactly like the others and call the vectorized or scalar interface in order to process the track or the particle within tracker or within a calorimeter or whatever. Yes. But besides from the interface, the core of this work is to provide a tool that could use machine learning techniques. So you will see that we plan to test different of them to replace the standard Monte Carlo approach. So the idea would be to choose a model, to do the training using information from your detector and the particle types, the kinematics, whatever it is, that the kind of events that you want to simulate, and get your trained model, and from there use it to generate the events. So initially, this is the part that we'd like to provide within GeantV. So we would like to be able, our interface, to be able to call through this generic interface whatever model that could be trained to generate events or to do the simulation for a specific detector. And there are some things that should be considered. That one of the things that we're starting to look at in order to from a practical point of view, in order to actually make this happen, is how we are going to convert the trained neural network, something that could be easily compatible with C++ applications such as there are options. One possibility is this, one possibility is this library, LWTNN, that's been being developed within Atlas. It is actually now not really a possibility, it's an example of what we would like to have. This converts networks in JSON file, and this can be loaded into the C++ application. Unfortunately, this library for now does not implement conversion for convolutional layers, which is the core of our network. So it's not something we can use, but it's this style of libraries that we are looking for. There is an additional step, of course. If you want, what is really important about this project is that later on, we would like to actually include in GeantV the whole training process. And the idea being that we want to be able to choose our model from the input, from the kind of detector that we'd like to simulate, so to take this into account from the very beginning, so already at this step, and provide a tool that would be capable of optimizing this configuration and do the training from inside the GeantV structure. So using basically on the fly the simulated events. The first step for us, of course, because this is all, if you want, it's a long-term plan. The first step is, of course, to prove that all of this is possible and to start with the design of the machine learning model itself. So to start this work, we decided to focus, of course, on most time-consuming detectors. For experiments like ATLAS or CMS, calorimeters are, of course, such detectors. And start working on the training the networks on full simulated events, so basically GeantV events currently. But we also would like to have to test eventually the possibility of training on using real data. We also want to look at different techniques and different models. And the work that we started doing right now is to look at how generative adversarial networks work. But of course, there could be problems, simulation, for example, of tracking detectors or other detectors that could be better solved using different techniques. So for example, recurrent networks are also another technique that we'll probably be looking at later on. So I will show you the work we've been doing on generative adversarial network. And again, you've seen this. I don't need to go through again. Let me just say again that when you're training a generative adversarial network, in case any of you wasn't here on Tuesday morning, you are training two networks. One, that is the generator, and it's reproducing events that look like your data distribution starting from a random variable, a random vector called the latent vector. And those generated samples are compared to the real images and classified by the second network as real or fake. And this is an iterative process that goes on until the generator is capable of producing images that are so close to the real ones that the discriminator is unable to distinguish them anymore. And again, this is also something I showed, and I show it again because this is the kind of architecture that we have implemented in our case. We are looking at auxiliary classifier GANs. It means that in addition to the picture that you saw until now, we are also an additional task classifying the events that are generated by the generator as belonging to a specific class. So for our work, we use the data, the simulation of a click calorimeter. So you know click is a project that's a CERN for a linear accelerator. And there is an associated study on detector design that goes with it. And so the calorimeter for this here is the reference. The calorimeter is an example of a high granularity calorimeter. It's the reason why we are interested in that. And there is an electromagnetic part and a hadronic part. For the beginning of this work, we are still just looking at the electromagnetic part. We will introduce the hadronic at a second stage. What's good about this data, this model, is that the data has been released between the CERN Open Data Initiative, so it's available for everyone to use. And in particular, the data sets that were generated with GeantV through the DD4 app framework. So there's two kinds of them: energy distribution, fixed energy. Those are simplified data simulations, if you want, of meaning that, for example, there is no clustering algorithm applied, no clustering ID applied. There is just the response of the detectors that from GeantV has output of GeantV of the simulation just looks like that, and it turns once it's pixelized into something like this. So basically, you have your colorimeter, your electromagnetic colorimeter that is pixelized, segmented in the X, Y, and Z dimensions in 25 pixels, and there is the hadronic colorimeter that has a different segmentation in the 3 dimensions. So basically, you have your primary particle that enters in, it deposits energy in the electromagnetic colorimeters, and then go on. And the color codes are representing the intensity of the energy deposited in the cell, the amount of energy that's deposited in the cells. Once you do this pixelization, your data is basically a 3-dimensional image. So how do we do this? We build the conditional GAN. And we, well, yeah, actually, we don't simply do conditioning. As I mentioned, these are auxiliary classifiers. We're also asking for the discriminator to tell us what kind of particles we fed in. Those are convolutions, and the convolution layers, the convolutions are done directly in 3D. There are several how should I say, techniques that should be used if you want to try to train efficiently GANs. Some of those, we tried a lot of things. Some of those were helpful for us, and we have implemented. Others were not so helpful. It's interesting, for example, to see that almost all works, all people that have been training GANs around use the ADAM optimizer. This doesn't really work for us. Anyway, we do our training in batches, and we use cross entropy as a loss. Those are the architectures of the two networks, and those are some results. Those networks are the results are obtained. Yeah. Oh, yes. I'm speaking very slow. Sorry. Those are obtained training the network using 150,000 events. Those are electrons and photons, and for fixed energy values. And this is, for example, those are 2 example images. This is the longitudinal section of the shower. You can see that it's slightly off. Those are also shower transfer sections for Y and X. The bulk of the distribution is not that bad. This is in log scale. The tails are still not well described here, especially in some at the very end. But we also check the single cell response. We really want to have images that look as real as possible. So basically what happens is that if you look at cells where the energy deposited is large, the networks manage to reproduce it very well. If you're looking at cells where the energy deposition is much smaller, basically you are here, then the response is not so good. If we put the energy in, and so instead of looking at different kind of particles, we look at the energy, and we train on a large continuous spectrum, then we are using energy as an auxiliary classifier, and it turns out that this is helping the work of our network. This is the same plot I showed you before. It gets better once we train including the energy. And this is true also for the transverse profile. You can see that you go, for example, for the X directions from this situation to this, so the bulk of the distribution is much better. The situation on the tails is comparable. We also check the energy regression. This is the results that we get for the central values, so values that are well contained in the spectrum. We get orders that are below, we have errors that are below 10%. If we go closer to the edges of the training spectrum, the situation is not so good. Anyway, I would like to stress that this is kind of a consistency check. We are checking what the discriminator tells us about the energy, but this is not the point of actually making this exercise. So the next step, of course, we would like to have an example that is ready by the end of the year, which means that we have a lot of work to do, because we are still working on the optimization. And in particular, we want to understand what is the best way to train this network. Do we want to train like we did with the continuous spectrum and then use this to generate events at specific energies, which would be, for example, a real case? Or would it be better to train it on single points and then do interpolation, extrapolation? We need to compare. We also, to have a figure of how well or how bad we are doing, we want to compare to other fast simulation approach, because so far you saw results compared to a full sim, and generalize to a multi-class approach. And this is important because we want to be able to vary different quantities that describe your particle. One word about the timing. It's nice to see that, well, I think the fact that the inference step is much faster than any other kind of algorithm approach, I think it's assumed. On my laptop, which has an Intel i7 core, it took only 66 milliseconds to get a shower, fully simulated. And it's a fraction of that, a small fraction of that if you're using a GPU. But the training time is also important. It's something that cannot be neglected. And it's specifically important if we want to work on embedded algorithms and really do the kind of optimization that we claim we want to do at some point. So being able to train and optimize the architecture of our, I'm done, of our model, depending on the kind of problem that we want to solve. So we are interested in testing how this is going to work when we run on large clusters. So as a summary, we are interested in a configurable framework for fast simulation. The idea is to be able to embed user code very easily and provide at the same time a reasonable list of algorithms that could be used. The idea is to include also tools that are based on machine learning, and we started evaluating and optimizing different models, well, one for now, but this also means that we are open to collaboration with other people that are interested in similar problems. So the integration in GeantV will happen in steps. We will have the inference step at first, and then the training tool. And let me just stress that this is something that we do within the GeantV context, but it's also something that could profit Geant for itself, because if we got something that works, it could be exported and used within their framework too. So thanks. Yes. Ah, that's perfect. You have a... That will be perfect. Yeah, we don't want to redo that ourselves, so we are... I generated 100,000... well, yeah, but I had... Yes, well, apart from the initialization, which is... But it's not... No, yes. Actually, I think on the GPU I run on 1 million events, so yeah. Not on my laptop.
At the moment, GeantV, even parametric models provide opportunity to get fluctuations. Each time when you play electromagnetic showers, you have different values of deposit energy and different distribution of this deposition in space. In your model, will you provide opportunity to have fluctuated showers?
Well, it all depends on what the network will learn. If I have a sample which fluctuations, then the network can learn from that, and then it can reproduce it. I have to have it in my training sample.
Do I understand correctly that your work will be implemented into GeantV as a standard feature?
It's one of the algorithms that GeantV will include in the interface for FastSim. Yes.
So, and do you plan to add fluctuation to your as a standard feature?
As I said, if we want to, if it's something that is needed, we need to have it in our training sample. We will train our networks to reproduce it, then it will be there.
So
It's not something.
yeah.
Okay, we can talk.
I'm not sure if I'm interpreting your question correctly, but I think like if you're worried about the network always outputting the same shower given the same energy and the same particle, that's actually taken care of by the fact that you start with random noise. So everything, yeah, the input to, yeah, exactly. Well, I mean, like I'm not sure like what you mean by fluctuation. Like, do you mean the fact that literally, yeah, if you request like a pion at 10 GeV, you could get from regular GeantV like, you know, all sorts of different pions at 10 GeV. And from the GAN, you can get the same. Or what sort of fluctuation are you talking about, I guess?
Yeah.
It's not clear to both of us, probably. Yeah, sure.
Okay.
Okay.